welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 877, Stone Game. This is a fascinating problem that combines strategy and recursion, and it's a great opportunity to sharpen your problem-solving skills. Let's dive in. In this problem, Alice and Bob are playing a game with an even number of piles of stones arranged in a row. Each pile contains a positive number of stones, and the total number of stones across all the piles is odd. This ensures that there can never be a tie in the game. Alice and Bob take turns, with Alice always starting first. On each turn, a player can choose to take stones from either the first pile or the last pile in the row. The game continues until all the piles are taken, and the player who collects the most stones wins. Since both players are assumed to play optimally, meaning they always make the best possible move to maximize their chances of winning, the goal is to determine if Alice can guarantee a win. If Alice wins, the function should return true, otherwise, it should return false. For example, consider the input piles equals 5, 3, 4, 5. In this case, Alice starts by taking the first pile, which has 5 stones, leaving piles equals 3, 4, 5. Bob then takes the last pile with 5 stones, leaving piles equals 3, 4. Next, Alice takes the last pile with 4 stones, leaving piles equals 3. Finally, Bob takes the remaining pile with 3 stones. At the end of the game, Alice has 5 plus 4 is equal to 9 stones, while Bob has 5 plus 3 is equal to 8 stones. Since Alice has more stones than Bob, the function returns true because Alice wins. Now, let's look at another example with piles equals 3, 7, 2, 3. In this case, Alice starts by taking the last pile, which has 3 stones, leaving piles equals 3, 7, 2. Bob then takes the first pile with 3 stones, leaving piles equals 7, 2. Alice then takes the first pile with 7 stones, leaving piles equals 2. Finally, Bob takes the remaining pile with 2 stones. By the end of the game, Alice has 3 plus 7 is equal to 10 stones, while Bob has 3 plus 2 is equal to 5 stones. Once again, Alice has more stones than Bob, so the function returns true. The constraints ensure that the total number of stones is always odd, guaranteeing a winner. Additionally, both players always play optimally, which means the solution must account for the best possible moves at every step. For smaller cases like 2 piles, Alice will always win by taking the larger pile. For larger cases, efficient algorithms are necessary since brute force approaches won't work well for up to 500 piles. To solve the stone game problem, one approach we can consider is using a brute force method based on recursion. The intuition here is to simulate all possible moves that Alice and Bob can make during the game. Since both players aim to maximize their scores, we can use recursion to explore every possible sequence of moves. At each step, the current player selects either the leftmost or the rightmost pile, and the game then continues recursively with the remaining piles. This approach relies on representing the game state as a range of indices, L, R, which denote the piles still in play. The recursion calculates the maximum score a player can achieve within this range, but this method is highly inefficient because it repeats calculations for overlapping subproblems. Specifically, the time complexity is exponential, O(2 to the power of n), where n is the number of piles, and the space complexity is O(n), due to the recursion stack. While this approach is conceptually straightforward, it is computationally prohibitive and unsuitable for larger inputs, making it impractical for this problem. To improve upon the brute force approach, we can use a dynamic programming strategy that eliminates redundant calculations by storing intermediate results. This optimization is possible because the problem exhibits overlapping subproblems. We define dp, L, R, as the maximum difference in scores the current player can achieve over their opponent when playing with the piles in the range, L, R. On each turn, the current player has 2 choices: select the leftmost pile, piles, L, or the rightmost pile, piles, R. After making a choice, the remaining piles are updated to L plus 1, R, or L, R1, respectively. The key formula for this transition is dp, L, R, equals max, piles, L, dp, L plus 1, R, piles, R, dp, L, R1. The base case occurs when there is only one pile left, in which case dp, I equals piles, I. Using this approach, the result for the entire game can be found in dp, 0, and 1, representing the full range of piles. By leveraging dynamic programming, we significantly reduce the computational complexity compared to the naive recursive approach. The dynamic programming approach offers a significant improvement in efficiency, with a time complexity of O(n) squared and a space complexity of O(n) squared, where n is the number of piles. This is because we fill out a two-dimensional DP table, where each cell represents the solution for a specific range of piles. However, despite being efficient, this solution is more complex than necessary given the constraints of the problem. This leads us to consider an optimized mathematical approach. The key insight here is that the problem guarantees an even number of piles and an odd total number of stones, which ensures that no tie is possible. Since Alice always plays first, she can guarantee a win by strategically choosing piles. Specifically, Alice can evaluate the total stones in the even-indexed and odd-indexed piles and always pick from the group with the higher total. This deterministic nature of the problem allows us to conclude that Alice will always win, making this approach both intuitive and efficient. The optimized mathematical approach is the most efficient solution for this problem, with a time complexity of O(1) and a space complexity of O(1). By leveraging the guarantees provided in the problem statement, we can directly conclude that Alice will always win and return true without performing any complex computations. This approach was chosen because it is the simplest and most efficient solution. While the dynamic programming approach is elegant and generalizable to variations of the problem, it is unnecessary given the deterministic nature of this specific scenario. On the other hand, the brute force approach, while conceptually simple, is computationally infeasible. The trade-offs are clear. The optimized mathematical approach is extremely efficient but lacks applicability to other problem variations, whereas dynamic programming balances efficiency and generalizability. Ultimately, directly returning true avoids unnecessary computation and achieves optimal runtime and space efficiency, making it the best choice for this problem. In this problem, we are dealing with a competitive game between two players, Alice and Bob. They take turns picking elements from an array, aiming to maximize their respective scores. Alice always goes first, and both players play optimally, meaning they make decisions that maximize or minimize the game outcome depending on whose turn it is. To solve this, we start by defining a recursive function, which we'll call maxScore. This function will simulate the game's progress by considering the current playable range of the array, a flag to indicate whose turn it is, and a memoization table to store results. The base case for the recursion is straightforward. If the playable range becomes invalid, meaning no elements are left to pick, the score is 0. For the recursive case, we analyze the decisions each player can make. When it's Alice's turn, she has two options: pick the element at the leftmost end or the rightmost end of the array. For each choice, we simulate the rest of the game, assuming Bob will play optimally in the subsequent turn. This sets the foundation for our solution. Once Alice has simulated both possible moves, picking from the left or the right, we calculate her potential score for each choice. Her score is the value of the element she picks plus the result of the next game state. Since Alice is trying to maximize her score, we take the maximum of both options. On the other hand, when it's Bob's turn, he follows a similar approach. He can pick an element from either the left or the right end of the playable range, and for each choice, the game progresses with Alice playing optimally in the next state. However, Bob's goal is to minimize the score Alice can achieve, so we take the minimum score from both of Bob's choices. To make this algorithm efficient, we use memoization. By storing the result of each subproblem max score (YL, R, turn) in a table, we can avoid recalculating the same values repeatedly, which significantly reduces computational overhead. Finally, we initialize the algorithm by calling maxScore with the entire array in Alice's turn, and the result of this call gives us the answer to the problem. The recursive approach can be further optimized using the memoization table. This table, which is a 2D array or dictionary, stores the result of each subproblem for a given range of indices and player turn. For example, dp L, R contains the solution for the range L, R. This data structure helps us avoid redundant calculations by reusing previously computed results. The input array itself remains unchanged and simply represents the elements Alice and Bob can pick from. In terms of complexity, the time complexity of the algorithm is O(n) squared, where n is the length of the array. This is because there are n squared subproblems, one for each possible range, L, R, and each subproblem is solved in constant time. The space complexity is also n squared, as we need to store the results for all subproblems in our memoization table. Now, let's consider some edge cases. In a single-element array, Alice picks the only element, and Bob scores 0. If all elements in the array are equal, both players end up with the same score since they play optimally. Finally, if the array is empty, the result is 0, as there are no elements to pick. With this understanding, we can now look at the pseudocode implementation of the recursive solution. The implementation begins with the recursive helper function maxScore. If the range L, R is invalid, meaning L greater than R, we return 0, as no elements are left to pick. Next, we check the memoization table. If the result for the current state is already stored, we return that value to avoid recomputation. For Alice's turn, we calculate her score by simulating both choices, picking the leftmost element or the rightmost. Her score for each choice is the value of the picked element plus the recursive result of the next state, where it's Bob's turn. We store the maximum of these two scores in the memoization table. For Bob, we follow a similar process, but instead of maximizing the score, we minimize it, as Bob's strategy is to limit Alice's score. Once the recursive function is fully defined, we initialize the array, its length, and the memoization table. The function is then called with the entire array range and Alice's turn to compute the result. This implementation ensures that all overlapping subproblems are solved efficiently, giving us the final answer in n squared, time and space complexity. This solution uses dynamic programming to solve the stone game problem optimally. The goal is to determine if Alice, playing first, can win given that both players play optimally. The core of the solution revolves around a two-dimensional DP table, dp, I, j. Here, dp, I, j represents the maximum score difference the current player can achieve over the opponent when considering the subarray piles, I, j. ### explanation of the code. 1. Initialization asterisk. The length of the input array piles is stored in n. A DP table DP of size nxn is initialized with zeros, where dp, I, j will represent the maximum score difference the current player can achieve when playing the subarray piles, I, j. 2. Base case asterisk. If a player is left with just one pile, when I = j, the only option is to take that pile. Therefore, dp, I equals piles, I. 3. Filling the DP table asterisk. The table is filled for subarray lengths ranging from 2 to n. For each subarray defined by indices I and j, the current player has two optimal choices. Take the leftmost pile, piles, I, and let the opponent play on the subarray piles, I plus 1 and j. The resulting score difference is piles, I, dp, I plus 1, j. Take the rightmost pile, piles, j, and let the opponent play on the subarray piles, I, j1. The resulting score difference is piles, j, dp, I, j1. The optimal choice for the current player is the maximum of these two options, so dp, I, j equals max, piles, I, dp, I plus 1, j, piles, j, dp, I, j1. 4. Final result asterisk. After filling the table, the value dp, 0, and 1, the entire range of the array, represents the maximum score difference Alice can achieve if she plays optimally. If this value is positive, it means Alice can win, so we return true. Otherwise, we return false. ### complexity. Time complexity asterisk. The solution involves filling a DP table of size nxn, and each entry takes constant time to compute. Hence, the overall time complexity is n squared. Space complexity asterisk. The space complexity is n squared, due to the DP table. This approach is both efficient and optimal for the given problem constraints. This is the Java implementation of the stone game problem, LeetCode number 877, which mirrors the logic of the provided Python solution. It uses a dynamic programming approach to calculate the maximum difference in stones a player can achieve by making optimal moves. The main differences in Java include explicit type declarations, the use of Java arrays for the DP table, and the math library for maximum calculations. To solve the stone game problem, we start by initializing the necessary variables. The input array is piles equals 5, 3, 4, 5, and its length is n equals 4. Next, we create a 2D dynamic programming table dp initialized to zeros. This table will store the maximum difference in scores that the first player can achieve over the second player for any subarray of piles. The base case is when the subarray contains just one pile, so we fill the diagonal of the dp table with the respective pile values, as the first player will always take the only pile available. The resulting table looks like this: 5, 0, 0, 0, 0, 3, 0, 0, 0, 0, 4, 0, 0, 0, 0, 5. This sets up the foundation for filling out the rest of the table and solving the problem iteratively. Now, we proceed to fill the dp table for subarrays of increasing lengths. For subarrays of length 2, we calculate the maximum difference in scores the first player can achieve based on the piles they can pick and the results of the smaller subarrays. For example, dp 0, 1 is calculated as max piles 0, dp 1, 1 piles 1, dp 0, 0, which evaluates to 2. Similarly, we calculate dp 1, 2 as 1 and dp 2, 3 as 1. Moving to subarrays of length 3, we again compute the values using the same logic. For example, dp 0, 2 is 4 and dp 1, 3 is also 4. The updated dp table is now 5, 2, 4, 0, 0, 3, 1, 4, 0, 0, 4, 1, 0, 0, 0, 5. By breaking the problem into smaller subproblems, we build up solutions for larger subarrays systematically. For subarrays of length 4, which span the entire array, we calculate dp 0, 3 using the same approach. The formula dp 0, 3 equals max piles 0, dp 1, 3 piles 3, dp 0, 2 gives us a result of 1. This means the first player can achieve a score difference of 1 over the second player if both play optimally. Finally, the result of the game is determined by the value of dp 0 and 1, which is dp 0, 3. Since this value is greater than 0, the first player has a winning strategy. Therefore, the output for this example is true, indicating that the first player wins. In the second example, we follow the same approach with piles equals 3, 7, 2, 3. The length of the array is n equals 4, and we again initialize a 2D dp table with zeros. The base case involves filling the diagonal of the table with the values from piles, as each pile represents the score a player can get when only one pile is available. After this step, the dp table looks like this: 3, 0, 0, 0, 0, 7, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3. From here, we will fill the table for subarrays of increasing lengths using the same logic as before. For subarrays of length 2, we calculate values like dp 0, 1, which equals 4, as well as dp 1, 2, and dp 2, 3, which are 5 and 1, respectively. For subarrays of length 3, we compute values such as dp 0, 2 equals -1 and dp 1, 3 equals 6. Finally, for subarrays of length 4, we calculate dp 0, 3 equals 4. This means the first player can achieve a score difference of 4 over the second player for the entire array. The updated dp table is 3, 4, -1, 4, 0, 7, 5, 6, 0, 0, 2, 1, 0, 0, 0, 3. These calculations help us determine the winner based on the final value of the table. The final decision is determined by dp 0 and 1, which is dp 0, 3 equals 4. Since this value is greater than 0, it indicates that the first player has a winning strategy when both players play optimally. Thus, the output for this example is true, confirming that the first player wins. With this, we have successfully demonstrated how dynamic programming enables us to solve the stone game problem efficiently. In the stone game problem, we use dynamic programming to calculate the maximum number of stones a player can collect from any subarray of the piles. This involves creating a 2D dp table, where each entry dp I, j, represents the optimal score from the subarray starting at index I and ending at index j. To build this table, we first initialize it. The table has dimensions nxn, where n is the number of piles, and initializing it takes n squared time since we need to allocate memory for all entries. Next, we populate the base cases. Specifically, for any pile I, the value dp I is set to piles I, because if there's only one pile in the subarray, the player can simply take all the stones in that pile. Since there are n piles, this step takes n time. These two steps set the stage for filling out the rest of the table, which we'll look at next. To fill the DP table, we systematically consider subarrays of increasing lengths, starting from length 2 up to the full length of the array. For each subarray length, the outer loop determines the length of the subarray we are evaluating, and this loop runs n1 times, corresponding to lengths from 2 to n. Inside this loop, we iterate over all starting indices I such that the subarray fits within the bounds of the array. The number of iterations of this inner loop decreases as the subarray length increases, but the total across all lengths remains proportional to n. Within each iteration of the inner loop, we calculate the value of dp ij by considering the maximum score the player can achieve by choosing either the left or right pile in the subarray. This operation is constant, O1, since it involves a simple comparison. When you sum up all these operations across the various subarray lengths, the total work is equivalent to the sum of the first n1 integers, which is n1 n/2. This simplifies to n squared time complexity for this step. After the DP table is fully populated, the final step is to make a single comparison, checking whether dp 0 n1 is greater than 0. This tells us whether the first player can ensure a win given optimal play. Since this is just one operation, it takes O1 time. Collectively, the initialization, base case population, table filling, and final comparison result in an overall time complexity of n squared. Moving on to space complexity, the most significant factor is the DP table itself, which is a 2D list with dimensions nxn. Since each entry is a constant-sized integer, the total space required for the table is n squared. Additionally, we use a few auxiliary variables for indexing and loop control, but these only require constant space, O1. No recursion or additional data structures are used, so the overall space complexity remains n squared. When comparing the dynamic programming approach to a brute force solution, the efficiency gain becomes evident. A naive recursive solution would involve exploring every possible sequence of moves, where each decision branches into two new possibilities. This results in a total of 2n combinations to evaluate, yielding an exponential time complexity of O2 to the power of n. Such an approach quickly becomes impractical for larger inputs. In contrast, the DP approach leverages overlapping subproblems in memoization, ensuring that each subproblem is solved only once. By storing intermediate results in the DP table, redundant calculations are avoided entirely, reducing the time complexity from exponential to n squared. This dramatic improvement makes the DP solution far more suitable for real-world scenarios. The quadratic time complexity of n squared is a direct result of iterating through all possible subarray pairs, I, j, where 0 equals I less than j less than n. For every valid pair, we calculate the optimal score once and store it in the DP table. Since the number of such pairs is exactly n1/2, the time complexity scales quadratically with the size of the input. Similarly, the space complexity is n squared, because the DP table requires quadratically increasing memory as the size of n grows. In summary, the DP approach provides a practical solution to the stone game problem, delivering a time complexity of n squared and a space complexity of n squared, while being exponentially faster than a brute force solution. This efficiency underscores the power of dynamic programming in solving optimization problems efficiently. When solving recursion problems like stone game, there are a few common mistakes to watch out for. First, ignoring base cases in recursion can lead to infinite recursion or incorrect results. For example, if the problem reduces to an empty array or only one element and you haven't explicitly defined what should happen in these scenarios, your solution will break. The fix is simple: always define clear stopping conditions for your recursion. Second, not using memoization is another frequent issue. Recursive solutions that don't store the results of previously solved subproblems tend to recompute the same values over and over again, leading to exponential time complexity. By incorporating a memoization table, such as a dictionary or a 2D array, you can store these results and avoid redundant calculations. Lastly, overlooking edge cases can cause your solution to fail in unexpected ways. Think about arrays with all equal elements, extremely large or small inputs, or just one element. Testing against a variety of edge cases ensures your solution is robust and handles all scenarios correctly. Another common pitfall is managing the player turn logic incorrectly. In problems with alternating turns, like Stone Game, it's essential to keep track of whose turn it is, whether it's Alice or Bob. Mismanaging this can throw off your score calculations. To avoid this, clearly define the turn logic and ensure it alternates properly in each recursive call or iteration. Additionally, time complexity is a critical factor to consider. Brute force solutions might pass smaller test cases but fail on larger inputs due to their inefficiency, often operating at 2 to the power of n, or worse. To address this, analyze the problem carefully and optimize using dynamic programming, iterative methods, or pruning techniques to make your solution scalable. Now, let's dive into some interview-specific insights. Recursion problems often have two key properties: overlapping subproblems and optimal substructure, making them ideal candidates for dynamic programming. Breaking the problem into smaller components can help you identify these patterns. In two-player games like Stone Game, understanding how each player can maximize or minimize their score is critical. Simulating both players' moves and choosing the best possible outcome ensures your solution is optimal. Another consideration is the trade-off between time and space. While dynamic programming can greatly reduce computation time, it often requires significant memory. You can optimize space by reducing a 2D DP array to a 1D array if intermediate results don't need to be stored. Lastly, during interviews, it's crucial to articulate your thought process. Explain how you're using recursion or dynamic programming, highlight your base cases, describe state transitions, and emphasize how memoization avoids redundant computations. Clear communication can make a big difference in demonstrating your understanding. Stone Game is not the only problem that leverages recursion and dynamic programming. For example, Stone Game 2 builds on the original by introducing additional constraints, making the problem more challenging. Predict the Winner is another problem that uses dynamic programming to determine if the first player can guarantee a win with optimal play. Beyond two-player games, LeetCode 1312, Minimum Insertion Steps to Make a String Palindrome, showcases how dynamic programming applies to different domains, such as string manipulation, by solving overlapping subproblems. Exploring related problems like these provides a deeper understanding of how these techniques can be adapted to different scenarios. Finally, let's explore some alternative approaches. One common method is iterative dynamic programming. While it avoids the risk of recursion stack overflow and can be easier to debug, it often requires careful indexing to manage transitions between states. This is especially helpful when recursion depth becomes a concern. Another approach is the minimax algorithm with pruning. Although it adds complexity by requiring logic to prune unnecessary branches, it's invaluable for solving problems with deep state space trees, particularly in competitive settings. Lastly, greedy approaches can sometimes provide a simpler solution. However, they only work when the problem guarantees that local optimization leads to the global solution. This makes them faster but unsuitable for problems that require a more comprehensive exploration of possibilities. By understanding these trade-offs, you can choose the best approach for the problem at hand. Great job following along. We've covered the Stone Game problem, explored its brute force recursion approach, and discussed key takeaways for tackling similar problems. Don't forget to practice more, and we'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!